For each positive integer n, let xn be a real number in the open interval 0 to 1 over n. Which of the following statements must be true? Okay, and we're given 3 statements here and some possible combination of them, which could be true. Questions like this, I'd like to just go through each statement one at a time and try and justify whether they are correct or not. So let's look at statement number 1. Okay. Well, let me give the background. We've got xn is between 0 and 1 over n, open interval. So statement 1 is that the limit as n approaches infinity of xn equals 0. This is definitely true. I mean, we have that xn is less than 1 over n between 0. You can think of this sort of like a squeeze type thing. This clearly approaches 0 as n goes to infinity, and this being bounded below by 0 means it must also go to 0. So that's a pretty easy one. Number 2. Ooh, okay. If f is continuous, so f maps 0, 1 to r, then f of xn is Cauchy. This is also going to be true because, wait. Hold on. Okay. If f were defined on the closed interval, then this would be true. But f is not defined at 0. So let me get rid of that. I think I can probably come up with a counterexample to this pretty easily. Let's, simply let xn be equal to 1 over 2n. And let's let f of x be equal to, like log of x? Then f of xn clearly goes to negative infinity. And if it were a Cauchy sequence, it would have to converge, and this does not converge. Okay, so number 2 is false. Yeah, if f were defined, if it had a closed endpoint there, and f of 0 existed, then we could make some arguments about, continuity, limits, and all that stuff. But it's not. So let's move on to number 3. G maps 0, 1 to r, uniformly continuous. Then the limit as the limit as n goes to infinity of g of xn exists. G is uniformly continuous. I'm tempted to say that this is true, but I'm going to put a check mark with a question mark and see if I can just prove it. So I have that xn is less than epsilon for all n greater than or equal to capital N. There exists capital N, well, let me put it this way. For all epsilon, there exists a capital N where this statement holds. So I need but it's a little bit difficult without knowing what the limit is going to be, right? Maybe I can just prove that this is a Cauchy sequence instead. So let's fix epsilon greater than 0. This is less than well, I'm going to have two epsilons, epsilon 1 and epsilon 2. This is less than epsilon 1 if n and m are greater than or equal to some capital N, unrelated to the things up there. So, so how do I have something like this? Well, I know that my original sequence converges, and so it's Cauchy. And so maybe I should, instead of epsilon 1, let's fix a delta greater than 0. And in fact, let's fix epsilon, which then gives us a corresponding delta greater than 0, which is like the delta coming from the uniform continuity of G. So there exists an n such that xn minus xm is less than delta for all n and m greater than or equal to n. Okay, so again, my original sequence converges, therefore it's Cauchy. If it's Cauchy, if I have any delta, I can find an n such that this is true. So fix epsilon, that implies a delta from uniform continuity of G. I choose n such that this is less than delta. Because this is the delta that comes from the epsilon, this must be less than epsilon. And so I've proven that G of xn is Cauchy, and therefore converges. So 3 is true. And the answer here should be 1 and 3, which is option C. Yeah, I'm happy that I didn't jump the gun too quickly on number 2. And I mean, I've sort of skipped. I've at least said everything. You know, all the information to prove that number 3 is true is sitting here. Maybe I didn't organize it the best, but that's kind of what happens when you try these things live. If I wanted to rewrite this proof so that it could be read line for line pretty directly, now that I have it in my head, that wouldn't be too difficult to organize. But yeah, my answer will be C. If there's a mistake somewhere, I'll be certain to highlight it in the video or write it down in the description. Thanks for watching.